Okay, this is paper 3, 2019, number 4. This question is about forces and momentum. In a high school physics laboratory, 2 trolleys were used on a friction compensated ramp. That just means that we can ignore friction to determine the mass of trolley 2. Figure 4.1 shows the diagram of the experimental setup. The vibrating pin has a frequency of 50 Hertz. This means that it makes 50 ticks per second. Okay, so we can have a look at the diagram. After giving a slight push, trolley 1, moving at a constant speed and having a mass of 1,250 grams, attached to a ticker tape timer, moves down the incline and collides with a stationary trolley of unknown mass. They are coupled after collision and move off together with a constant velocity. All right, so that is a mouthful. Make sure that we understand everything that's going on here. Okay. So this is the vibrating pin that makes marks on the carbon paper here, and it's going to give us a reading like this. So that would be what the carbon paper would look like after being passed through the ticker tape timer. And the tape is connected to trolley 1. So it's mapping out the motion of trolley 1. Trolley 1 is going to have a collision with trolley 2, which is not moving initially. Okay, so trolley 1 is moving down the ramp. Trolley 2 is still. All right, so this is a conservation of momentum problem initially. So the first thing we're asked to do is state the principle of conservation of linear momentum. Okay, so state the law of conservation or the principle of conservation of momentum. So we're looking for this statement, which says, if no external forces act on 2 objects that collide, momentum is conserved. Okay, so that's a very simple way of stating it. What I want to point out is that this first part here is very important. This is your qualifier. Okay, so this statement is only true if no external forces are acting on them. So the only 2 forces that are acting are the forces that the 2 objects exert on each other when they collide. Momentum is conserved. What that means is that the momentum of the objects before, okay, or rather the sum of the object's momentum does not change. That's what that means. Okay, that does not mean that their speed doesn't change. Okay, obviously if something stationary gets hit by something that's moving, then it will start moving itself if they are of comparable size. So one thing will stop moving and the other thing will start moving, or they will both move at a different velocity. So this statement does not mean that the objects are not moving. It just means that when you add up their momentum, which is the product of their mass and velocity, that you will get the same sum before and after the collision. Okay, so whichever way you are comfortable stating that or summarizing that, you can go ahead and do that. Okay, but these are your keywords here. You got to have this qualifier. If no external forces act, momentum is conserved. If that's all you can remember, then you're good. If no external forces act, momentum is conserved. You'll get your 1 point for that. All right, so now we're having a look at the output of the ticker tape used in the experiment. So after the crash, we pull out the tape and we look at it, and we can tell a couple of things from the spacing of the dots on this tape. So first of all, we're asked to point out the point on the tape where the objects would have collided, where trolley 1 hit trolley 2. Okay, so initially trolley 1 would have been moving down the ramp. Okay, let's just go back and make sure that we read everything our question says. Yes, trolley 1 would have been moving down at constant speed. Okay, what that looks like on a ticker tape, that means that all the dots would have been equally spaced because it's covering the same amount of distance every time the ticker needle goes down. Okay, if it was moving faster and faster, then we would see our dots getting closer and closer together. Okay, think about if you're trying to carry a bucket or a bowl that has a hole at the bottom. The slower you walk, then you're going to have more water on the floor. Think about, so if trolley 1 was moving faster, then what we would see is wider spaces between the dots. Okay? Think about if you have a cup with a hole in it and you're trying to quickly get it, over the sink or something. The faster you move, the less likely it is you'll end up with a lot of water on the floor. But if you take your sweet time and you're just walking, you're going to have a lot of water on the floor. Think of the water on the floor as the dots on the tape. The faster you move, the less dots on the tape. The slower you move, the more dots on the tape. Okay, and if you are moving at a constant speed, then your dots are going to be equally spread out. Okay, so the first part of the tape is where trolley 1 is moving at a constant speed. We start to see a change in the distance between the dots now when trolley, at this point here, okay? And what's happening after that? We see the dots get further spaced out. So that means that trolley 1, if you said that means trolley 1 got faster, then you would be correct. Okay? So let's work that out. We're done with that. Next thing we're asked is to calculate the speed of trolley 1 before the collision. Okay, so we want to know what is the speed before this point. How can we figure that out? To calculate speed, we need to know a couple of things. We need to know the distance covered, and we need to know the time taken. How do we find the distance covered? Well, in a question like this, if you're not given the length between the dots, then you have to literally take your ruler and measure it. So you won't be able to do that by doing this online, but when you're in the exam, you would do that. So bring your ruler to physics exam. Okay, so you'll have to measure that, and if you had this paper and you printed it out and you measured it, you would get about 4.5 centimeters. If you measure the length from here to here, 4.5 centimeters. And then how do I figure out the time? Okay, you have to go back to the beginning, back to the question. This little piece right here tells you about the time. You don't see the word time anywhere here, but here's where you have to remember something from a different topic. You have to remember what the definition of frequency is. Frequency is the amount of times an event occurs per second. Okay, and that in this case, it's the amount of times the pin hits the carbon paper per second. So having a frequency of 50 hertz means that the pin comes down every 50th of a second. Okay, and that works out to about 0.02 seconds. Okay, All right. This is pretty standard in all of the questions about ticker tape timers that you're going to get. This is the time. So the time elapsed between each dot, no matter how far apart they are, is 0.02 seconds. So to figure out how much time has passed, all you need to do is count the amount of spaces, not dots, okay? The amount of spaces. So from here to here, okay, so from here to here is 0.02 seconds. That's another 0.02 seconds, and we go 3, 4, 5, 6, 7, 8, 9 spaces. Okay, and each one of those spaces correspond to 0.02 seconds. And so when we work that out, we're going to get 4.5 centimeters divided by 9 times 0.02, which works out to 0.18 seconds. And so the speed, we're going to state in centimeters per second, that's fine, 25 centimeters per second. That is the speed of trolley 1 before collision. The next part of the question asks us to calculate the speed of the coupled trolleys after collision. Coupled mean that they stick together and they move with the same speed. So they both will have the same speed after the collision. Now to figure this part out, we have to go back to the tape, because if this here marked the point of collision, then that means the rest of the tape is the motion of the trolleys when they're moving together. So we need to figure out now what is the speed for this part of the tape. So again, we're going to count the spaces. We're going to take our ruler and we're going to measure the length. So we need the length from this dot, the one right where the collision started, to the last one. Okay, let's put that in a different color so you're clear where we are starting and stopping. Okay, first dot, last dot, we need the length. So take your ruler and measure between those 2 points. And then we're going to count the number of spaces. That's going to give us our time. The time elapsed between each dot is 0.02. So it goes 1, 2, 3, 4, 5, 6, 7, 8. Remember, we're counting spaces, not dots, okay? So there are 8 spaces between those 2 dots. So that means we're going to go back down here. We're going to use the same formula that we used to calculate the speed of trolley 1 for the first part of the tape. And we're going to repeat that process. So the speed of the coupled trolleys is going to be equal to, and I'm going to write this out so you can have a generic formula. So the length of tape divided by number of spaces times 0.02. That's not going to change. As long as you see 50 hertz, then the time between the 2 dots is 0.02. Okay, if you see 40 hertz, then you just say 1 divided by 40 and you'll get the time. All right, so length of tape, I measured it and I got about 8 centimeters. And 8 spaces multiplied by 0.02, that works out to 8 centimeters divided by 0.16 seconds. And so our speed is equal to 50 centimeters per second. Okay. So the speed increased And then finally, the last part of the question asks us to determine the mass of trolley 2 using our results from part B1 and part B2. Let's remind ourselves what our results from those parts were. Okay, so B1, that should probably say B2 and 3. So I think that's what we're meant to use here. So let's write that down on the side here. The speed of trolley 1, so speed of trolley 1 before the collision is equal to 25 centimeters per second. So we're writing down what we know. We also know that the mass of trolley 1 is equal to 1,250 grams. What else do we know? We also know that their common speed, so the velocity of trolleys 1 and 2 after the collision is equal to 50 centimeters per second. What can we do with that? We need another equation, the very, very long equation, but it's nothing we can't handle, right? All right, so let's start by writing out our equation. Okay. And I'm going to simplify it a bit by just writing momentum. So let's remind ourselves what momentum means first. Momentum is equal to mass multiplied by velocity. The principle of conservation of linear momentum, written mathematically, says that the momentum of object 1 plus the momentum of object 2 before the collision is equal to the momentum of object 1 plus the momentum of object 2 after the collision. Now, let's work out what each of these are, and then we'll make it really simple for ourselves. So let's call trolley 1, that's object 1. What is the momentum of object 1 before the collision? Well, it has a mass of 1,250 grams multiplied by its speed, which we know to be 25 centimeters. And that works out to, take your calculators and you can plug that in, 1250 multiplied by 25 gives us a momentum of 250. Okay. Then the momentum of object 2, trolley 2, before the collision, well, that was 0 because it was stationary, it wasn't moving. What about after the collision? Well, after the collision, the momentum of trolley 1 would be its mass, which is still 1,250 grams, multiplied by its new speed now, which is 50. And that works out to 62,500. And then finally, the momentum of trolley 2 after the collision, we're going to have to write as an expression because we don't know its mass. We want to solve for its mass. So remember that momentum is mass times velocity. So we're going to leave the m there for mass. That's going to be mass of object 2. But we know that its speed after is 50. So we can write it like this. Okay. You can write it more algebraically, a little more conventional. So we say 50 times its mass. Okay. And so things that we don't need to write in here, we can make this really simple. We don't need to write that in because that term goes away. We can replace the momentum of object 1 before with this value, 31250, and that's equal to the momentum of object 1 after, which we can replace with this value that we've already worked out, 62500. And then we're going to put back our expression for the momentum of object 2 after, 50 m2. And so now it's just a very simple linear equation we have to solve. Okay, so we're going to do that. Going to take the 62 over to the other side, and we're going to work that out. And so when we work this out, we find that the mass is equal to, we take this subtraction, take this over to the other side, this becomes 31250 minus 62500. Our 50 is still here. Well, that's twice that. When we work that out, we see we get 50 m equals 31250. And then the last step is just to divide both sides by 50. 31250 over 50, and that gives us 625 grams as the mass of object 2. And that's it. Okay, the last question in this asks, what physical quantity represents the rate of change of momentum? So this is a definition here. The rate of change of momentum. What we're looking for here is for you to recognize this relationship. Rate of change of momentum is actually equal to force. Okay? That's what we're looking for. And that's the end of this question.